Hello, I'm very excited to be talking to you today about the black holes that lurk at the centers of galaxies. So if you look up at the night sky, somewhere in the Virgo constellation, about 55 million light years away from us, there's a galaxy called M87. This galaxy is very bright in optical light. You can see it with your telescope. It looks just like a star. But with very powerful optical and radio telescopes, you can actually start to see a lot of streams of light coming from the center of the galaxy. This stream of light is actually powered by a black hole billions of times more massive than our sun. With radio waves, we can peer through everything between us and the center of the galaxy and follow this stream of light all the way to its origin, the supermassive black hole M87 star. This was the first picture of a black hole ever taken by the Event Horizon Telescope, and I'll be telling you a little bit about our story and why this is important for us to understand these objects. So let's start with just what is a black hole? So an object's escape velocity is independent of its mass. So any object trying to escape the gravitational pull of the Earth would have the same escape velocity. It would need the same speed to escape the pull of the Earth. Whether it is a bowling ball or a feather, it would need to go at the same speed to leave the Earth's gravity. So in 1784, there was this Reverend John Mitchell who thought about this interesting thought experiment. He sort of asked, how small does an object like the Earth or a star need to be for its escape velocity to be faster than the speed of light, such that light could no longer escape its gravity? Once the escape velocity exceeds the speed of light, even photons, which are the particles of light, will be trapped, and this object would become dark. So the star, if we would collapse it all the way down for it to have an escape velocity higher than the speed of light, it would become what he called a dark star. And this is sort of the first rough idea that came about that would later lead to the objects that we call black holes. In 1915, Albert Einstein published his general theory of relativity that predicts that light is affected by gravity. And in fact, in his theory, he showed that the curvature of space is caused by massive objects. So if you have a very massive object curving space-time, light would actually go on bended paths around it. This was first observed by an expedition led by Arthur Eddington in 1919, where they observed the bended path of starlight around the sun during a solar eclipse. In 1916, another physicist, Carl Schwarzschild, discovers the first proper solution to Einstein's theory, which leads to this object that depends on a particular radius, which he called the Schwarzschild radius. And this radius delimits the boundary at which the escape speed to leave the gravitational pull of this object would become higher than the speed of light. This boundary is what we now call the event horizon. In 1916, another physicist called David Hilbert publishes what he called the Foundation of Physics. And in this book, he is the first to calculate how a black hole would look to a distant observer. And in fact, it casts a shadow with a diameter of about 5 times larger than the Schwarzschild radius. This is because the light that travel all the way to an observer bend a little further out from the black hole than the light that would fall in. Here's a little schematic of how this works. So here's the black hole at the center bending space-time. And the red circle here is the event horizon. So you see light rays that come hole bend around because of the gravity of the black hole. So no matter where the light rays come from, they always bend and travel all the way to the distant observer, to our camera. And they form this bright ring of light with a dark patch in the center. The dark patch is what we call the black hole shadow. In 1931 came another astronomer, Subramanian Chandrasekhar. He was actually working with Arthur Eddington on the evolution of stars. And he discovers that the end point of stars, as understood back then, white dwarfs, actually have a maximum mass. So heavy stars, much more massive than the ones that would collapse into white dwarfs, must have another type of endpoint. And so this was the first time that black holes were really thought of outside of a mathematical context. They are thought of now as real astrophysical objects that could be the death of heavy stars, the inevitable endpoint of heavier stars. So stars are born in what we call stellar nebulae. They're basically birth centers for stars. And average mass stars, like our sun, they go through a life cycle in which they live a long life as a solar mass star, like our sun, and then they expand into a red giant, and they collapse into what we call a planetary nebula at the end of their lifetime. At the center of this planetary nebula is a white dwarf. Now, if stars are more massive, these massive stars, they end their life by blowing up into a red supergiant compared to a red giant, much larger. And this red supergiant, eventually its core is going to collapse on itself because it's too heavy, and it explodes in a supernova. And at the center, this really, really heavy core that collapsed can either collapse into a neutron star or, in the more massive cases, a black hole. And these are what we call stellar mass black holes. These are the types of black holes that we can now observe for, creating gravitational waves as they merge with each other. But there's other types of black holes, much bigger ones, that are also very interesting in astrophysics and lurk in our universe. So supermassive black holes actually reside at the centers of most galaxies. In the early 1900s, there was a start of discovery of thin streams of light coming from centers of galaxies. In those times, these galaxies were not really thought of as galaxies. They were called nebulae, but they were indeed just entire galaxies that are so bright with starlight, and there's thin streams of matter coming from it. As telescopes become more and more developed, we started seeing these streams in radio waves, in X-ray, in infrared, in optical light. And so these kinds of incredible composite astronomical images came about. These cosmic lighthouses, they are enormous. The little stars at the center of these big streams, these jets, are entire galaxies. These jets are so huge, they go through incredibly large distances away from the galaxy. And right at the center of it, at the core engine, is thought to be a supermassive black hole, millions to billions of times more massive than our sun. But in terms of scale, this black hole is really tiny compared to the entire galaxy it lives in. And yet, it creates this huge lighthouse that blows gas and radiation across entire galaxies and galaxy neighborhoods. And in fact, this process is believed to be quite important for the evolution of galaxies and how stars form in different galaxies, because the radiation usually falls back onto the galaxies and regulate how stars form and how many stars can form. And so the symbiotic relationship, this close-knit relationship between the black hole and its host galaxy, is quite critical for us to understand in order to fully understand our role here in the universe. And so black holes really play a fundamental role in these processes, in our story in the universe. So understanding how black holes create these jets, why they form, how they form, why do they exist at the centers of galaxies, are key questions that we want to answer in astrophysics and as part of the Event Horizon Telescope. So the Event Horizon Telescope, or the EHT, is what we call a radio telescope. So radio astronomy is a type of astronomy across the electromagnetic spectrum that focuses on radio waves from the sky. And so we collect them with these kinds of radio dishes that look like telecom dishes compared to mirrors that are typically in optical telescopes. So why is it nice to observe in radio? It's because radio waves are quite long compared to optical. And so they're not affected by dust. We can look through anything. And so we can look deeply into centers of galaxies. And the higher the frequency we go in radio waves, the more radiation we see very close to the black hole. The higher the frequency, the higher the resolution of our telescope as well. So of course, we're looking for black holes at the centers of the galaxies, the ones that would be big enough on the sky to make an image of. And it turns out that we might as well just go to our closest black hole. So we live in the Milky Way galaxy, so let's have a look at our center of our Milky Way. In the Sagittarius constellation is the galactic center, the center of the Milky Way galaxy. And this is a very crowded environment full of stars and gas, where stars are born and die. And in this environment, thanks to radio waves, we can look through all of this stuff, all of this very busy and dynamical stuff, all the way to its center, and go to higher and higher frequency and unveil the supermassive black hole called Sagittarius A star. This image was published by the EHT back in 2022, and it is the first look at the black hole in our Milky Way. Sagittarius A star is a very interesting black hole because it's actually very common. It lives in our Milky Way galaxy, which is a spiral galaxy, a very small spiral galaxy. And it's quite common because a lot of galaxies are spiral galaxies. And it's quite on the small side of the supermassive black hole range. It's 4 million times more massive than our sun. It is the largest black hole in the sky as seen from Earth because it is quite close to us, only 26,000 light years. Its size on the sky is about 50 microarc seconds. Or to give a sense of it, it's like the size of an orange on the moon as seen from Earth. And so the telescope needed in order to see this would need the resolution to basically pick out mustard seeds in Los Angeles while being in New York City. That's the resolution of the EHT. Now I already talked about the M87 black hole, but let's take another look at this one. So compared to Sagittarius A star, which is quite close and lives in our galaxy and is fairly quiet, M87 is actually one of these cosmic lighthouses. And in fact, it is the very first astrophysical jet ever observed by astronomers back in 1918. And so this stream of light, this bright jet of plasma, is ejected by the supermassive black hole itself. And we're trying to understand this process. M87 is actually much larger. The galaxy is a large elliptical galaxy compared to our Milky Way spiral galaxy. And its supermassive black hole is 6.5 billion times the mass of the sun. It's actually one of the largest black holes we have observed in our local universe. So M87 is over 1,000 times more massive than Sag A star, but it's also over 1,000 times further away. It's 55 million light years away, which makes it the second largest black hole in the sky as seen from Earth. So it has an angular size of about 40 microarc seconds, or the size of an apple on the moon as seen from Earth. So a telescope with the resolution of the EHT would be able to see the black hole. So why is the EHT the way it is? How big must our telescope be? Why do we need this amount of resolution to see anything? So the size of a telescope is proportional to the observing wavelength that we look at divided by the angular resolution that we want for our image. So we have a predicted size of about 20 to 40 microarc seconds for black holes, and so the angular resolution is 20 microarc seconds. The observing wavelength is actually a short wavelength in the radio regime, which is 1.3 millimeters. At this wavelength, we can peer through everything and only see the highest energy gas very, very close to the black hole. So if we do this calculation, it turns out that our telescope will need to be 13 million meters wide. Now, that's a really big telescope, and it's very hard to convince people to fund and build something like that. But it turns out we can use tricks because there is something that's accessible to us that is 13 million meters wide, and that is planet Earth. And so the Event Horizon Telescope is not a physical telescope the size of the Earth. It's a computational telescope made up by connecting several telescopes around the globe to form a telescope the size of the Earth through computers. And so by collecting data at different telescopes, we can create an image. I'll show you a little bit how we do this. So the EHT uses a technique called very long baseline interferometry. I won't go into too much detail, but I just want to demo you a little bit how it works in practice. So we have our black hole very, very far away. The photons emitted around the black hole, the radio waves, are from glowing hot gas. And because the black hole is very far away, the waves that arrive are flat. They're plane waves. And you'll notice that the waves actually arrive at the lower telescope first before it reaches the higher telescope because of the curvature of the Earth. In order to make an image, we need multiple telescopes at different locations on the Earth. We call the distance between two telescopes a baseline distance, and each pair of telescopes is a baseline. In order to sample different information on our image, we need baseline distances that are at different lengths and also different orientations on the Earth in order to be able to sample different scales on our image. Short spacings give us large scale, long spacings give us small scale, and then different directions give us information on different crossings across our image. Now, because there is a different time of arrival of our signal at different telescopes, in order to connect each of the signals that we receive, we really need to be very careful about the time difference of the arrival of the signal at our telescopes, because we want to align the black hole signals. So we actually use very accurate atomic clocks. These are so accurate, they lose about a second every million years. And we time tag the data with very, very high precision timing and record it onto hard drives. This allows us to freeze the light onto our hard drives and play it back at a later time in a supercomputer where we align all of the signals. After a lot of data processing, understanding all the different effects in our telescopes, we can then make an image. In 2017 was the first fully fledged observations of the EHT that allowed imaging. We had 8 different telescopes at 6 geographic locations. Since then, the EHT has grown, and it has now 4 new telescopes in 2025, and it still observes every year. You'll notice all of these telescopes look very, very different from each other. It's because they were built for different types of science. We essentially just borrow them for the EHT and equip them with our recording equipment in order to carry out our observations. All of these telescopes are at very high and dry places because the Earth's atmosphere actually scrambles and absorbs our black hole signal. So we need very, very dry and stable atmospheric conditions, which leads us to be on mountaintops and deserts and even the North and South Pole in order to carry out our observations. In order to make an image, we use a technique called aperture synthesis. The Earth's rotation actually helps us a ton in order to fill our virtual mirror of our virtual telescope. We can combine data on different times and different spatial scales because of this sampling. So here, as M87 becomes visible to stations as the Earth rotates, each of our pairs of telescopes, baselines, have different lengths and different directions. So we're sampling different parts of our mirror. And as we fill up our mirror over an entire observing night, we can stack data over that time, and our image becomes better and better as we stack data. You see here, we basically see nothing with a few data points, and then as we fill up our coverage, our mirror, we get the image structure popping quicker and quicker. And then we obtain our final image over one night of observations. So these are the images of M87 and Sagittarius as done by the Event Horizon Telescope. We published M87 in 2019, Sagittarius A** in 2022. Now, I already talked a little bit about the differences in in these two black holes. They live in very different galaxy environments. They're in very different masses. M87 has a big jet come out of it, and Sagittarius star doesn't seem to have one. Sagittarius star also eats gas matter much slower than M87. Yet they look very, very similar to each other. This is because gravity is what dominates the image that we see of the black holes. As we get very, very close to the black holes, what we're really seeing is the shadow and the bending of these light rays around the black hole itself that creates this ring of light. Now, just to give you a sense of scale between the two black holes, the shadow of M87 could hold our entire solar system. In fact, Voyager 1, which is the furthest human-made object launched into space, would just graze its edge right now. That's how big M87 is. 6.5 billion times more massive than our sun. Sagittarius A star, our Milky Way black hole, in comparison, is only snugly fitting into the orbit of Mercury. So it's much smaller, only 4 million times the mass of our sun. To give more physical scales, if Sagittarius A star were the size of a donut, M87 would be the size of a football stadium. Now we also, the light that we collect is actually polarized light. So I'm going to play this little video to explain, that we made to explain how we, why polarization is interesting and why it's important for us to understand how black holes work.
What is polarization? Light bouncing off objects allows us to see them. Light is an oscillating electromagnetic wave. We see different frequencies of that oscillation as different colors. The electric field component of a light wave can oscillate in any direction perpendicular to the direction of travel. Light from the sun oscillates in all directions. We say it is unpolarized. If the waves have a preferred direction of oscillation, they are polarized. For example, light from your phone is vertically polarized. Your polarized sunglasses are a polarized filter. Here, they let vertical polarization through. If we rotate them, almost all the polarized light gets blocked. Light produced by a torch is unpolarized. When we place a polarized filter in between, the light becomes polarized. In space, randomly moving hot gas or plasma emits unpolarized light, like the torch. Plasma threaded by a magnetic field is ordered and the emitted light is polarized. The magnetic field acts as a polarized filter. The strong gravity near a black hole bends the magnetic field and twists the polarization direction of the light from the surrounding plasma. The polarized light rays that manage to escape travel to a distant camera. The intensity of the light rays and their direction are what we observe with the Event Horizon Telescope. Using this knowledge, we can map out the magnetic fields that surround black holes.
So in 2021 and then 2024 for Sagittarius star, we published the polarized images of our two black holes. And these add sort of streaks of polarization direction on top of our images. And these streaks of polarization of the direction of oscillation of light actually infers information about the magnetic fields that thread the black holes. These magnetic fields are believed to be what drives the feeding and the ejection of plasma, of matter, around black holes. And it turns out that in both cases, we're seeing spiral-shaped magnetic fields that are quite strong and ordered. This is very puzzling because we really think these types of spiral, strong magnetic fields are what drives and launches the jet in M87. But Sagittarius A star doesn't seem to have a jet, so why does it have this type of magnetic field? Now, these two black holes are so different that we think that maybe this type of magnetic field structure is common to all black holes. Maybe it's just a universal feature of how black holes feed. This would be a very interesting result for us to have. And this is a rough idea of how black holes are meant to be feeding and how theorists think about the environment around black holes. So we have a black hole at the center And because of its gravity, there's matter orbiting and falling into the black hole. It's orbiting at such high speeds that it's basically ions. It's charged plasma, charged gas. And there are magnetic fields threading this gas that go and basically govern how the black hole feeds and how the jet is launched. And then there's matter falling into the black hole and then ejected through these big jets. And electrons swirling around magnetic fields actually get accelerated and emit light. And this is the light that we observe, that we collect with the Event Horizon Telescope to make images. So this is our rough understanding currently of how black holes work. And this is how it is in reality. This is Centaurus A, a very famous radio galaxy. You can see the galaxy dust there, and you can see the two big jets of plasma coming out from the galaxy. These are caused by the black hole central engine. So black holes really are cosmic lighthouses. Understanding this process also means that we need to observe these black holes more frequently. Not only do we want to see static images of them, we want to see them move. We want to see the dynamical process. We also want to go to higher resolution and make sharper images of black holes, maybe extending the EHT further than Earth into space. And these are very cool projects that are upcoming in the next few years. So lots of cool things coming out of the EHT. So if you want to stay tuned, please go take a look at our social media and our website. We have a lot of really cool educational videos also that are useful in our YouTube channel. Thank you very much.